we need to plot the graph of this equation 4, right? So equation 4 implies is r is equals to minus kt plus r naught. Now we know in one mathematical equations y is equals to mx plus c. So if I plot the graph of this equation, this coordinate x, the y, so this origin, so here what we get is a this type of curve, okay, and this is your constant. So this much height from here to here is a c, and what is slope? Slope is m, right, in this equation. So this represents the slope. Since it's a positive plus m, so we have a progressive slope, so it's increasing, right? Slope is increasing, positive slope, right? And c is the intercept, and y is, so only two variables are there, y and x. So as the x changes, the value of y changes. M is slope is a constant, and c is also constant. Now if you compare this here are two factors. This is a rate constant and this is the initial constant. This two factor doesn't change, so only the changing factor is time and the concentration of the reactant. So as the time increases, the concentration of the reactant decreases, right? So these two factors decreases. So see, if we, so here t is compared to x and r is compared to y. So if I plot the graph here, but remember there is a negative one, so it's a negative slope, right? So 0, so here is okay, this is t, or this is or we can write something like this also, right? Concentration, square bracket represents the concentration, okay, we'll just write this better. Okay, so the graph will be something like this, downward slope, and this intercept value is your r0, okay, initial concentration, intercept. So this much 0 to this much height is your r0, okay, intercept value, and the slope, so SL slope is your minus k, so it's a decreasing slope, fine. Next important thing we have to learn is the half-life of the reaction. So what is half-life of the reaction? So half-life is the time taken by the reaction to reach its initial concentration to exactly to half. Okay, so if we start with the 5 gram, then the time taken to reach 2.5 gram, okay, exactly the half time, half of its initial weight, okay. So that is the half-life of a reaction. So we have already discussed this is the final equation, integrated rate equation for zero order reaction, right? So at half-life, so we can write that t, we just write t equals to t half, and half-life, what will be the concentration? We have already mentioned it is a half the initial one, right? So initial is r0, so we'll just replace these two factor, rt equals to half and r equals to r0 by 2 in this equation. This is for zero order. Remember half-life for, we are talking about zero order reaction, right? So we'll substitute. So equation 6 implies, so t half is equals to r0 minus, now r is replaced by r0 by 2, whole divided by k is here, right? So if I do the so it's a we can say also, if we do the LCM and then everything, so it's a, you'll find it that it is a r0 by 2 by k, okay. So if solve it, then it will be r0 by 2k, so t half. So equation 7, right? So final equation, it comes as a t half is equals to r0 by 2k. So the half-life period for the zero order reaction is r0, the initial concentration, divided by 2 times the rate constant. Next we will learn about the integrated rate equation of for first order reaction. So in the syllabus we just have zero order and first order reaction. Okay, so for integrated, so first for first order reaction, n equals to 1, okay. So as the reaction goes to the product, then we know rate is equals to minus dr by dt. So this is the integrated equation, and another from the rate law expression we get it is a minus, no, it's the k, sorry, it's k r to the power 1, right? So since it's a first order reaction, so it's a k r to the power 1. So equation 2. Now we're just comparing the equation 1 and equation 2. We get that minus dr by dt is equals to k to the power r, right? Since this is a perfect differential, so we can take dt in this side and we'll just put this r here. So r minus dr by this r is equals to k dt, and we'll just take this negative here also, so it will be something like this. So equation 3. Now integrating this equation by integrating both sides the above equation, we get, so integration of dr by r is equals to, so this is constant, so we'll just take it out, dt, right? So this one, now 1 by r is your ln natural log, okay, r and some constant is there, equals to this minus k, this comes as a t plus, we'll put this c, constant, equation 4. Since integration of dx by x is equals to ln x plus c, we know, and integration of dx is equals to x plus c. We have learned this one, right? We'll continue with this one. So these are the reason we have mentioned, okay? So this also gives dr by r gives ln x, ln is natural log x, natural logs r, okay? So we have this is the general formula. So there is one constant, another, so here is also one, it also gives one constant, and this also gives one constant, right? Multiplied by minus k is also there. So altogether this constant has been kept as a c, okay? So we have to find the value of c here now. And initially when time t equals to 0, what is the concentration of r? We know it's a r0, okay? So substituting this value in the equation 4, so equation 4 implies here is ln, so r is replaced by r0 equals to minus k, t is replaced by 0 now, plus c, okay? So this implies c constant equals to ln r0, so equation 5. Now again equation 4, so we're just substituting the c equals to ln r0 in the equation 4. So equation 4 implies ln r is equals to minus k t plus c, c means your ln r0, fine. To equation 6, I'm putting lots of equation because these equations is further required, okay? Now okay, I'll take this ln 0 here, so or ln r, if I place here, so it gives ln r0 is equals to minus k t. So we know the properties of log, okay? So ln x minus ln y can be written as ln x by y, so we'll just use that property here by, okay, so this is minus kt. Since we know that ln x minus ln y can be written as a ln x by y, Okay, so these are the properties of the logarithm. Okay, these are given in the appendix of your textbook. So this is again your equation 7. Equation 7. Now if I remove this natural log, then your equation comes as a r by r0 equals to e is exponential to the power kt, right? So everything will come in the power. Since we have the property that ln x, if we have ln x equals to a, then we can write a equals to e to the power a. Okay, so this is the formula. Okay, this can be written as a x e to the power a. Fine. So if I keep here only the r, so we get is a r 0 e to the power minus k t. So this is one of the equation 8. We can derive another equation from the equation number 6. Okay, equation number 6. So at time t is equals to t1, what is the concentration of r? We just mention r equals to r1, right? r1. Then the equation 6 implies t equals to t1. Okay, so we have to replace this t equals to t1 and your r is r1. It has one advantage of using this equation. So ln r1 is equals to minus k t1 plus ln r0, right? Okay, so equation where we have reached equation 8, so we will just write equation 9. Similarly at time t is equals to t2, r is equals to r2, we'll just put it now. So what we get again, equation 6 implies ln r2 is equals to minus k t2 plus ln r0. Okay, so time जति प्रोग्रेस हुँदै जान्छ त्यति नै खाली r मात्रै चेन्ज हुन्छ नि त, अरू फ्याक्टर चेन्ज हुँदैन, इट्स इनिशियल कन्सन्ट्रेसन यो चेन्ज हुँदैन, राइट? क्वेसन 10. Okay, so by subtracting equation 10 from equation 9, we get okay, so equation 10 लाई चाहिँ equation 9 बाट घटाउनु, that means left hand सँग घट्छ, right? right hand सँग घट्छ, right? Okay, so from भने चाहिँ so equation 9 अगाडि बस्छ है. So ln अगाडि पछाडि भन्दा केही हुँदैन, हुनु चाहिँ minus ln r2 is equals to, this is minus kt1 plus ln r0 minus everything, this one minus kt2 plus ln r0, right? So if I minus kt1, that is plus ln r0, it's minus is plus, kt2 minus means minus ln r0. Okay, so this will cut. So what ultimately what we get is minus kt1 plus kt2. Here this we can say that okay, again utilizing this one formula 1 by r2, since we know that ln x minus ln y is equals to ln x by y. Fine. Okay, so further I'll just take this one, ln r1 by r2 is equals to, I'm taking the k common, okay, so positive k common, so that means t2 minus t1, okay, minus t1 plus. Fine, so I'll just take the key and k here, so everything goes here, so it's 1 by t2 minus t1 ln r 1 by r2, right? So this is the equation 11. Now advantage of this equation is that no, it doesn't have initial concentration. So if we measure, if we can able to measure the concentration at time t1 and again the concentration at time t2, okay, this is r2, then we can calculate the rate constant. अब इनिशियलमा जो कति अमाउन्टदेखि रिएक्सन भएको छ त्यो हामीलाई चाहिएन यसमा चाहिँ, त्यो आफ्टर 10 मिनट्स, ओके 10 मिनट चाहिँ यो कन्सन्ट्रेसन थियो र आफ्टर 20 मिनट चाहिँ यो कन्सन्ट्रेसन थियो भनेपछि वी क्यान क्यालकुलेट द चाहिँ यसमा इनिसियल कन्सन्ट्रेसन छैन. नाउ वी हेभ टु रिप्लेस दिस ln विथ द log with the base 10. So k is equals to 1 by t2 minus t1 log log. So log means 2.303. So 2.303 log r 1 by r2 ounce. La. So this is one of the important equations, equation 12. So I must write here that ln x can be written as 2.303 log x. Okay. There is one more derivation from the equation 6. Okay. That's it. Okay. So equation 6 implies यो k लाई यता ल्याए त k t is equals to l उता लाग्यो भने ln r 0 minus ln r हुन्छ. Okay. So kp is equals to, we have already learned that can be written as a r 0 by r. Fine. Now this one we'll just keep it k here. So k equals to 1 by t ln r 0 by r. Fine. So this is one equation. 13. Then we'll just change this ln with the log. So k is equals to 2.303 by t r 0 by, sorry, log log, forget it. So this is very important equation.